This is the June 2010 Regents Chemistry review of the multiple choice. Let's get started. Number 1. The gold foil experiment led to the conclusion that each atom in the foil was composed mostly of empty space because most alpha particles directed at the foil. Well, I keep playing the same video over and over again. I can't help but play it again. Okay, here we go. In all of its glory.
Volume, the atomic nucleus. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus. The particles were deflected by a high positive charge in a very small volume, the atomic nucleus.
So most of these went right through. Okay, when they got close to the positive nucleus, the positive alpha particle, which is 2 protons, got deflected, sometimes bounced back, but most of them went right through. Okay, so it's a famous gold foil experiment to prove that there's a nucleus of an atom where all its mass existed and with a positive charge. So in any case, most alpha particles directed at the foil passed through the foil. Okay, most were not deflected. If most were deflected, then we would say the nucleus was huge compared to the size of the atom. But because the nucleus of an atom is tiny, okay, most of these alpha particles would go through undetected. It's only in a very small occasions would they be close enough to deflect, and even fewer occasions where they would almost bounce back when it was almost a head-on collision. So therefore, most alpha particles to the floor passed through the foil to prove that most of the atom is empty space and that the nucleus is a small part of that space where all of its mass pretty much existed with a positive charge. Number 1. Which subatomic particles are located in the nucleus of a carbon atom? Well, carbon, most common isotope is carbon-12 because it rounds to that. Atomic number 6. All right, you should know that this gives me 6 protons because atomic number is 6 protons, and when you say an atom, it gives me 6 electrons, but they exist outside the nucleus. And to get your neutrons, 12 minus 6, 6 neutrons, right? This is the mass number. This is protons and neutrons. So you have 12 particles in there. Now they're not asking for particles, but you should know that protons and neutrons exist in the nucleus. That's where all the mass exists, which was deflecting the alpha particles in the Rutherford experiment. All right, and if you didn't know that they had mass, table O, okay, can show you that. Neutron has a mass of 1, right? And a proton has a mass of 1. That's where the mass number comes into play. And the entire mass of the atom is located in the nucleus of the atom. That's why there's empty space for these alpha particles to rush through. Now, of course, electrons exist here, and they give electrons a 0. Now, a beta particle is an electron, okay, another form of word, but we put a 0 here to show that it's insignificant compared to these masses. In fact, this thing is 2,000 times lighter. Back to the problems. So because they have mass, they are in the nucleus. Number 3. Okay. So question number 3, which part of the helium atom is positively charged? All these questions are going together. The nucleus, of course. Okay, the nucleus, in fact, an alpha particle is a helium nucleus. If you go back to table O, alpha particle is given this symbol, 4/2. Why? Because it is a helium nucleus. Okay, it's got 2 protons. That's what the 2 is here. Its atomic number is the proton number, and it's got a mass of 4. Well, why? There's 2 protons, 2 neutrons. As we've just talked about, neutrons and protons have the same mass. Okay, so it's a helium nucleus. So clearly the choice is 3. Not much more to talk about with that. Number 4. The mass of a proton is approximately equal to the mass of a neutron. Okay, all these questions are blending together. As I just discussed, table O, they both have that 1 above it. Okay, a proton, that's the different particles I get from table O, they both have a mass of 1. Now the neutron has a 0 here because it has no charge. Okay, a proton has a +1 charge. Number 5. Okay, and again, if you didn't get the other ones, but you should know the mass of a proton is equal to the mass of a neutron from table O. Okay, I should just show it any case. So I will. And there it is. They both have the same mass number. Number 5, at STP, solid carbon can exist as diamond and graphite. Compared to the molecular structure and chemical properties of diamond, graphite has, okay, well, graphite and diamond, it's not important you know the exact molecular structure, but they're both carbon. And diamond and graphite are clearly different types of the carbon. Diamond, of course, is that sparkling, very hard and possibly sharp, okay, crystalline form of carbon. Graphite's another crystalline form, but not nearly as hard. In fact, our pencils, okay, use graphite to write. Diamond, of course, can use as drill bits and jewelry, of course. However, there's no mistaking that diamond and graphite have two different properties. It's clearly. And you should know this very clearly. As I keep saying in many parts of my course, structure is king. You change the structure, you change the chemical and physical properties. So structure is king. So they have, because we know they have different properties, they must have different molecular structures. So choice 1 is the answer. Okay, different molecular structure, different properties. Okay, now in organic chemistry, okay, we talked about this a couple different ways. We showed you one propanol. Okay, prop means 3 carbons, 1 means OH, and the OL is an alcohol group. This is one propanol. And then I showed you 2 propanol. Well, these are isomers, right? There's a structural isomers. They have the same chemical formula, just different structure. This is C3, H1, 2, 3, 4, 5, 6, 7, 8, H8 with an O. This is also C3, H8 with the O. The dashes represent H's. Okay, so they have the same chemical formula, but they have different properties. Propanol is an alcohol that we could ingest. Okay, this 2-propanol, okay, is an alcohol that's very deadly. Okay, and of course these have 2 different properties, 2 different structures. Structure is king. Choice 1. Number 6. Number 6. Which group 14 element is classified as a metal? Well, group 14 just means that I'm in column 14. It's a family of elements. Okay, so I have to go to my periodic table. Now, metals are what most of the periodic table is made up of. They're the large ones, and they're usually below that staircase, that divider between metals and nonmetals. Let's go to the periodic table. Okay, here's our periodic table, and we should know that this dividing line, okay, that I'm tracing over, separates your metals. All of these are your metals, and your nonmetals. Nonmetals are the smaller ones, okay, above the staircase. These are smaller atoms that love to gain electrons. These are the big atoms that love to lose. How do you know? Look at the charges, party people. Look, these all become what? Positive. You become positive by losing negatives. These guys do not hold on to electrons loosely. These guys above the staircase can become negative because they love to gain electrons, because they attract electrons. The ones on the staircase here have properties of both metals and nonmetals, including germanium and antimony. They're the semi-metals or metalloids. But getting back to the question, group 14, this column, well, carbon is a nonmetal. It's above the staircase. Silicon and germanium are metalloids you should be aware of. And of course, tin is a metal. Okay? And you can see that below the staircase to the left, tin, as we know, is a metal. So let's go to the question. So carbon is our nonmetal. Silicon is our metalloid, or semi-metal, metalloid. And germanium is also the metalloid. The only one that's a metal is tin. Now you may say, Mr. Grotsky, how do I know tin is Sb? Well, let's go to another table, table S. How do I know it's tin? How do I know SN is tin? I might have said SB there. So how do I know that this is tin? Let's go to table S. So if you didn't know tin was SN, atomic number 50 right off the periodic table tells me tin is SN. Don't forget, table S shows you the elements names with the symbols if you need that. In this case, you might have. Okay, moving forward. The light emitted from a flame is produced when electrons in an excited state do what? Okay, well, this is a Bohr understanding. This is emission spectroscopy kind of a question. And I always draw the nucleus as positive. And let's draw electron positions away from the nucleus in shells. Now, they don't go in circular paths, but they are linked in energy by how far away they are from the nucleus. So we can make that analogy here. All right, so let's put an electron, okay, here, and an electron here. You should know electrons that are farther away are higher in energy. Okay, so higher in E. The ones that are closer are lower in energy. We would say these guys are stable. These are in their ground state. These guys, if they are farther away, are unstable, and they could be in excited state if they came from closer positions. Now, the atom is quantized. To get to an exact position, you need an exact amount of energy. But it should make sense to you that electrons that exist farther away need more energy to overcome the positive pulling force of the nucleus. So, you should know, in order for a typical light to be emitted, like the flame test you probably did in lab, you took a flame, okay, like a candle or a burner, okay, you put the sample over the flame, which probably was metal ions. Now you gave it energy. What happened was electrons from stable ground state positions were given energy from the flame enough to get to a certain level. They were excited at this position, and then they leaped back, and the extra energy they absorbed, right, because energy came in from the light, from the burner, so they absorbed energy to go farther away to overcome the positive pulling force of the nucleus, because low energy is stable. And then when they jumped back, they gave off energy in the form of electromagnetic radiation, hopefully in the visible spectrum or light, okay, to give up the extra energy they had. And once they give it up, so we're looking for light emitted from a flame is produce electrons in an excited state, okay, that's the state that we have high energy, okay, which means they must have jumped from their low energy state controlled by the nucleus, and now we're going to leap back to that low energy state, and they're going to release energy. Because think about it. If you didn't follow everything, light emitted means you gave off energy. So excited means you have high energy. So you're jumping back, okay, you're releasing energy, and they move to lower energy states. Okay? So clearly, electrons are leaping from this high energy excited state back to a low energy state. Stable means low energy. How do you go from high energy to low energy? You have to give it off. So electrons, when they jump backwards toward the nucleus, getting closer to the nucleus, have to give up their extra energy that allowed them to be farther away from the nucleus. Okay, so energy is emitted, you move to lower energy states which is closer to the nucleus. When energy is absorbed, you move farther away. You gained enough energy to take away to move away from. Analogy I used to use is, here's your mom and here's a kid. Okay, if you give a kid too much energy or give some energy, it can be farther away. Too much energy, it runs away. I don't know. Terrible analogy. Any case, number 8. An atom of which element has the greatest attraction for electrons? Okay, this is screaming attraction for electrons. You should know this to be electro negativity. Okay? So electronegativity. Something in there like that. Now, electronegativity, okay, is basically tied to the size of the atom. Smaller the atom, that means you attract that electron to that nucleus really well. Bigger atom, the electrons can exist farther away and be what? Higher energy, because they have more energy to overcome. That must mean that this doesn't have the energy. So the far electrons are, the more energy they have, right? Which means they're not attracted to the nucleus as well. It's a proximity thing. Back to the mom and the kid again. The closer the mom is to the kid, the less likely the kid is going to act up. But when the kid is farther away, from the mom, okay, then it's more likely this guy is going to do what he wants to do, beat his chest a little bit. So, in any case, back to the problem, okay? Who has the greatest attraction for electrons? I'm going to look and see where these guys are located on the periodic table first. So I have arsenic, gallium, germanium, selenium. Let's go to the periodic table. Okay, so I found my elements here. I got gallium, germanium, arsenic, and selenium. They're all right here. They're all in the same energy row. And I know something about the periodic table. As you go across in the same shell, the radius gets smaller, which means your attraction for your electrons has to increase. So just by understanding the periodic trends, selenium has the lowest electronegativity. That's it. Okay? Now, if you don't trust your periodic trends, you can go somewhere else to look. 31 through 34, who has the greatest electronegativity? Table S. Let's go there. Here's our table S. And let's go find our 4 elements that are in the row. And there they are. Gallium, germanium, arsenic, selenium. And look at this. The electronegativity goes from 1.8 to 2.0 to 2.2 to 2.6. As we go across the periodic table, the attractions increase because the radius gets smaller. Okay? Part of the reason there. So, back to the problem. Well, not quite. So, selenium, as I stated, based on the trends, being the farthest right of the 4 elements in the same period or row, is the most electronegative. So selenium is my answer. Let's go back to the problem. Now, whether you use the trends or you didn't trust yourself to know the trends, there's no reason to get this wrong. This is right off the periodic table, table S. Okay? And of course, you had to know attraction for electrons is electronegativity. Okay? Big one. Moving forward. So number 4 was for 8. Let's go to number 9. Which formula represents a polar molecule? Okay, to be polar molecule, that means that your molecule has a definite shape to it, has more electrons on one side of that shape or that molecule than another. So we say that this side would be negative and this side would be positive. Now it's really partial negative and positives because electrons aren't being transferred. But we have a scenario where we've got unequal distribution of electrons. Now, what causes that? Inside the molecule, something called polar bonds. Right, polar bonds, if you remember, are basically unequal sharing. Unequal sharing of electrons between atoms, between nonmetals. So, I need to have unequal sharing. Now, unequal sharing is tied to electronegativity. Okay? For instance, look at number 1 for a second. It's hydrogen, has 1 valence electron. The other hydrogen has another. They both get stable by having a configuration of 2, like their noble gas counterpart, helium. So they both feel like a helium having 2 electrons, which, by the way, fills the first energy level, so that's stable once you fill energy levels. So they both feel like helium by sharing 1 by each. Now they're forced to share because they both have pretty high electronegativities, and those electronegativities are 2.2 if you look at table S. Because they have the same attraction for electrons, these electrons are shared right down the middle, so they're sharing equally. Nobody on this side of the bond or this side of the bond has more electrons, so this is a nonpolar. These have nonpolar bonds. So these don't have any polar bonds, which means there's no place in the molecule where electrons are shared unequally, so this thing could never be a polar molecule. It has to have unequal sharing. Okay, let's look at CO2 for a second. Now CO2 looks like this. Carbon double bonded to an O, 2 lone pairs. And by the way, if you do enough of these tests, you see the same molecules over and over again. CO2. Now, CO2 does have polar bonds. How do I know? 2 different nonmetals. So it's sharing electrons unequally between the C and the O because you have 2 different electronegativities, 2 different atoms. So this has polar bonds. Okay, good. So this thing could be sharing unequally. However, because of symmetry being the same all the way around, we have the same unequal sharing on this side as we do this side. Therefore, there's no difference to this side and this side. There's no poles. Poles means you have differences. So this is a non-polar molecule with polar bonds because of the symmetry. So this is not a polar molecule. You have to keep the word polar molecule, polar bond separate. You need to have polar bonds to make a polar molecule. So this thing doesn't have differences. It has polar bonds, unequal sharing of electrons, but the symmetry again is being the same on both sides means that these same non-polar bonds, are the same on both sides, so there's no difference. Or we say the polar bonds cancel themselves out. If you have symmetry, then you can't be a polar molecule. Look at carbon tetrachloride, CCl4. Okay, that's 4 Cls. You've guessed it if I asked you, and I haven't asked you yet, so you couldn't have guessed it, but now I'm going to ask you, does this have polar bonds between the carbon and the Cl? Now, I should be drawing the rest of the dots. I'm just going to leave it like that. This is a polar bond. 2 different nonmetals, 2 different electronegativities, and they're sharing unequally. But because it's symmetrical, okay, there's no difference to one side or the other. All these unequal sharing are the same. So because of symmetry, this is a non-polar molecule. It has polar bonds, but because of the symmetry, the polar bonds are canceled. That leaves us with water, which you should know is polar for the millionth and one time. Water, here's its Lewis dot diagram. Oxygen has 6 valence. Okay, hydrogen has 1. Oxygen feels like it has 8 by sharing 2 more. Each hydrogen feels like it has 2, which fills the first energy level, makes it stable. Now, there is 2 polar bonds here, 2 different nonmetals sharing unequally. So this has a shot to be a polar molecule. There is an unequal distribution of electrons, but because this thing is not symmetrical, it's not the same all the way around, this unequal sharing exists within the molecule. And if I was to draw it, it looks something like this. A little horseshoe compound, terribly drawn, where there's more negatives in the oxygen than there is the H's, and the positives would be here and here. So this is a polar molecule. It has polar bonds, but the key thing here, it's asymmetrical. Okay, that allows the polar bonds to create an area. Okay, so number 9 is 2. A lot of explanations there, but you should know water is polar if you knew nothing else. Number 10. 2 categories of compounds are, well, the 2 basic types of bonding we have are covalent and ionic. The word for covalent is molecular. Now why? Because they make molecules. Ions, or ionic compounds, is the word. They make crystals of their ions. They do not make molecules. Molecules like water that we just drew, okay, number 9, has a distinct number of atoms and a distinct shape. Crystals have a repeating framework that keeps repeating over and over. The negatives attract the positives in a 3D arrangement. Oops, sorry. Okay, big fingers. Okay, so that's the difference here. So we call them molecular, is a fancy word for covalent. So this can't be the answer. This is covalent and covalent. Covalent and metallic. Okay, metallic represent metallic bonding. That's metals bonded to metals. But usually compounds, what we use in New York State Regents, compounds are what? Two or more different atoms. So metallic bonds are like copper bonding to copper, and the chemical formula would look like this for metallic. So therefore, for bonding copper to copper, that's not going to be considered a compound. It's going to be considered an element, right? If I have mercury in a thermometer or barometer, its chemical formula is this, mercury bonded to mercury. It's an element. So we're not going to use metallic. All right, ionic and molecular are how you make two or more different atoms. Okay, and that's the best answer, choice 3. Metallic, again, is really going to show how elements bond. Number 3 is 10 is 3. Number 11. Number 11 is tied to number 10. It's amazing how these questions kind of go together. What type of bond is between atoms of solid cobalt? Well, it's not going to be a compound, right? It's going to be cobalt bonded to cobalt. And that's metals bonded to metals. That's metallic bonding, as we just alluded to in number 10. So yeah, these go together. You should know metallic compounds have that C of mobile electrons. And they have the what? The chemical formula of just the element. So cobalt solid or copper solid. They're the atoms bonded to themselves. And they're called metallic bonds because, well, they're just metals kind of bonded to themselves, sharing their electrons in this sea of mobile electrons that able to give them their distinct property of great conductors of heat and electricity. Choice 3, metals bonding to metals is metallic. Number 12. Number 12, sublimation is a solid going directly to a gas. The two examples they seem to always go over is dry ice, CO2 solid, going to CO2 gas, or iodine. But if you didn't know that, you're looking for a solid going directly to a gas. And that's choice 1. A gas going directly into a solid is called deposition. It's not listed here, but it's one that could come up. So deposition and sublimation are those phase changes talked the least amount of the time. But sublimation is a solid going to a gas. Choice 1 is the answer. Solid to liquid, of course, is melting. Liquid going to gas is evaporation. And a liquid going to solid is freezing. Deposition, just so we make sure we don't forget this, is a gas going directly to a solid. An example of that is snowing. Yay. Okay. Number 13. Which sample of ethanol has particles with the highest average kinetic energy? You've got to know, party people, highest average kinetic energy means temperature. Temperature is the motion of particles. So, highest temperature is the highest average. So my friends in chemistry, the highest number, the highest average, choice 2. It's independent upon the size of the sample. I could have a class of 20 with an average of 80. I could have a class of 10 with an average of 90. What's the highest average? The highest number. Who cares how many? Of course, how many you have can make this number harder or more difficult to attain, but essentially an average is an average. We do not consider how much of the sample. We're not saying total energy. We want the average kinetic energy. That's what temperature measures. Okay, choice 2 is the answer. Okay, the molarity of an aqueous solution of sodium chloride is defined as, okay, well, if you don't know molarity, okay, it's given to you in table T, so let's go. So I'm looking at table T, scrolling down or looking down, and I see concentration in the middle of it. Okay, I see molarity, and molarity is moles of solute over liter of solution. That's simple. So it's moles of solute over liter of solution. Now, what makes it a little bit more challenging is that you're tempted to put grams, okay, but it's moles of solute. Now, solute is the substance being dissolved. Aqueous means you have water that is dissolving this solid or this solute. So the solute is the substance being dissolved, and it's dissolved in water. Water is the solvent. So it's the moles of solute, so the moles of NaCl, so it could be 3 or 4 at this point. Now it's not per liter of water, because if you remember your definition, it's liter of solution. Okay, that included the mass of the solute. So 4 is moles of solute per liter of solution. Don't fall for per liter of water. We do not make a molar concentration by taking a liter of water first and then trying to add stuff to it. If we do, it's because of Archimedes' principle and displacement, this liter solution will become greater than a liter. So we actually make molar solutions by adding the solid first, add some water to dissolve, right? And then once we dissolve it, add the water to the liter mark. Okay, so it's liter of solution. Choice 4 is the answer. Number 50. Okay, a real gas behaves like an ideal gas under which conditions? Well, if you remember, a real gas is like a real student, and an ideal gas is like an ideal student. Now, a real student is going to be attracted to his surroundings. Meaning, if I'm teaching a class and I got a real student, okay, he's going to be caring a lot about the people around him. He's going to talk to them. He's going to be social, okay. He might be trying to be social and attracted using social media during class, all those other things. And he's not focused on me. That, unfortunately, is a real student. Okay, an ideal student has no attractions, okay, for the people around him. Okay, he's focused on me, the teacher, like a falcon on prey. Any case, all right, so if I want to make a real gas that's really attracted to each other, okay, so there really is attractions between them, I want to behave least like an ideal gas. So a real has to be like an ideal gas. Now, ideal gas, I'm sorry, has no attractive. They're independent. They're actually kind of, these people are kind of, they're good students, but sometimes they could be very random because you ask them for a pencil or something, they'll say something like, hey, I like turtles. The problem is, because of their randomness, they have no attractions for other people. What makes them random is that they're independent particles. So let's read the question again before I get all excited with my analogies. A real gas behaves least like an ideal gas. So least like. So we want to have a real gas stay real, okay, and not have no attractions. So a real gas behaves least like an ideal gas. So how can I make this real gas stay like a real gas? Well, I can have them attract each other more by increasing the pressure. Increasing the pressure would push these closer together. So high pressure is what I would do here. Now, if I want to keep them having attractions and not paying attention to me, I also want to slow them down. So when they're moving slower, they have an opportunity to attract each other more. Remember, an ideal gas is going to go faster, and in low pressure have the least attractions, where a real gas is going to have some attractions where the temperature is dropped and the pressure increases. So in any case, I want to keep these real gases having attractions, so slower motion gives them an opportunity to attract each other, and high pressure forces them to attract each other or maintain these attractions at real gases. So a nice way to remember real gases first ideal is real gases, real student really has attractions to the people around him, and that ideal student, that super smart person who may be over the top with his schoolwork maybe, okay, is no attractions. I don't know, not trying to paint any stereotypes, just trying to make analogies that make sense for you guys. So any case, 15 is choice 2, okay? Number 16. Which sample of matter can be separated into different substances by a physical means? Okay, well, if I'm separating something physical, that means it was made physically. And I know that this solid here, for this to happen, there was a chemical bond between lithium and chlorine. This gas is a chemical bond between nitrogen and hydrogen because they're bonded. Same thing here. But the key to the problem for me is aqueous, and I should know that aqueous means homogeneous mixture. Why is it a mixture? Because I have lithium chloride mixed with water. Aqueous means mixed with water. And therefore, I can it was made by stirring a stirring rod with solid in a beaker. It was made physically. Now I can separate it by boiling off the water, and boiling off the water, okay, is a physical process because H2O liquid, if it goes to H2O gas, is still H2O. The chemical formula doesn't change. All the phase changes are physical. So we can separate mixtures, and we did. We took a sodium chloride mixture, we put it in an evaporating dish, and we boiled off the water and measured the dry compound. So choice 1 is the answer. Number 17. At STP, which is standard temperature and pressure, a liter of helium contains the same number of atoms as. Okay, this is Avogadro's hypothesis. And he stated that if you have equal volumes under the same conditions of temperature and pressure, and I'm going to assume that these two drawings are the same. Let's pretend this is 1 liter. Pretend this is 1 liter. I know we're pretending a lot, but pretend they're both at STP, or standard temperature and pressure. Okay, the number of gas molecules that fill this container will be the same. Same volume, okay, equals the same number of seats in a theater. That was my analogy earlier in the year. So if you're under the same conditions of temperature and pressure, temperature is motion and pressure is particles hitting each other, there's only a certain number of positions that gases can take up under the same conditions of temperature and pressure. I call it seats in a theater, but same volume, same number of molecules. That's Avogadro's hypothesis. So if I've got a liter of helium, it contains the same number of atoms, okay, as 1 liter of neon. Now they didn't use molecules, so we had to be careful there. Helium is monoatomic, okay, and if I have 22.4 liters, okay, of helium, I have something called 1 mole of helium, which is equal to 6.02 times 10 to the 23. Therefore, if I have a mole of neon, same number. But the bottom line here is same volume, same number of stuff that fits inside. This could have been a lot more trickier if they chose a different choice there, but straightforward answer there. Okay, sorry about the little bit of a delay. Okay, so number 17 is 1. Number 18. Which statement describes the particles of an ideal gas? An ideal gas, my friends, is a what? An ideal student. Ideal students, the most ideal. Okay? Ideal students are going to be random. They're paying attention to the teacher. Okay? You ask them to get something, they're going to move in a straight line pattern because they don't want to miss any of the lecture or any of the teaching going on. And they'll collide. Okay? So what I'm really asking of you is which of the following is something called part of the kinetic molecular theory? KMT is the acronym, or at least the shorthand notation. Kinetic molecular theory defines how gases should behave, ideally, and follow the gas laws. Exactly. Well, the gas laws are not perfect because most gases act real. Okay? In fact, we don't really have any ideal gases in nature, although there's conditions where they can become ideal. So back to the problem. All right? Let's go through the choices. Particles move in a well-defined circular paths. Well, circular paths, gases don't move in circular paths. And I think this is alluding to the Bohr model that state electrons move in circular paths, which we now know is not true. So that's not what we're talking about. When particles collide, energy is lost. Well, no, when these ideal gas students bump into people, that energy is transferred. Okay, it's never lost. If it was lost, we'd have implosions in tanks, so that can't be. Okay? There are forces of attraction between the particles. Ideal students, as we just talked about, another problem, ideal students do not have any attractions with the other students. Ideal gases don't have any attractions. That's why they are independent particles. Okay? So this is describing a real gas that really has attraction. So the best choice is 4. The volume of the particles is small. All right, so the kinetic molecular theory, this is the best answer. So to go through this, number 1, random. Okay, real gases, ideal students, ideal gases are random. 2, when they collide, and they do so, okay, energy is conserved. They call them elastic collisions. 3, they have no attractions. And 4, they typically have insignificant volume. Now they have some space they take up, but these ideal students tend to be smaller, okay? Tend to be faster, okay? Fast, small particles can be totally independent and not have any chance to attract. Slow-moving, bigger particles have a chance to attract. So when you think with me here, it's clear that 4 is the best choice. It describes one of the 4 postulates that gases must follow to follow the gas laws or be an ideal gas. Number 4 is the answer. Number 19, a chemical reaction occurs between iron atoms and oxygen atoms. Iron and oxygen, I'm thinking right away rust, right? Iron has electrons, oxygen wants them, okay? So oxidation, reduction, and we're going to make some rust, iron oxide of one compound that could be made. In any case, a chemical reaction is when bonds are being made or new bonds are made. Now, it can only occur if particles are heated. Well, not necessarily, because we know rust is formed, or a lot of reactions occur at cold temperatures. Atmospheric pressure decreases. Well, a lot of reactions will occur independent of the pressure changes, especially if they're solids or liquids. Only gases are affected by pressure. Catalyst present. Well, there's a lot of reactions that occur without a catalyst. If the activation energy is present, you should know all reactions are based upon collisions that are effective. And there's 2 things that make an effective collision. That's high enough kinetic energy, okay, to force the 2 atoms to collide. And of course, you have to have proper orientation so that, especially with bigger molecules, that the bonding sites are able to be hit. If the orientation isn't right, okay, then a reaction won't occur. Okay, case in point, ammonia has a lone pair of electrons. For it to bond to a proton, okay, that proton has to hit that part of the nitrogen. If not, it won't occur. So number 4 is the answer for number 19. Number 20. Given the equation representing a phase change at equilibrium. Oh, equilibrium, double arrow. 2 things I know. The rate of the forward equals the rate of the reverse, which means the solid melts as fast as the liquid freezes. Okay, now because of that scenario, the amount of solid and the amount of liquid stay constant. So those are 2 things. Okay, for instance, if I have a cooler, the best cooler of all time, and I put some water in it and I drop a big ice cube in it, okay, and it's a 1 kilogram ice cube, and I cover it so no heat gets in. Well, guess what? The temperature of the system will go to 0, and at that point, the rate of melting will equal the rate of refreezing. And over time, this square kilogram cube, okay, will change because some of it will melt, some of it will refreeze. It'll change its shape, but the 1 kilogram will stay constant. At equilibrium, the amount of each of the reactants and products has to stay constant. Another way to explain this, if I've got, let's say, 1, 2, 3, 4, 5 people on this line and 2 people on this line, and I say, okay, we're going to switch places evenly. Let's make the people on this line blue people, and we're going to say 1 person goes over here as 1 person goes over here every minute. Over time, how is this going to look? Well, the people are going to change positions, right? People are going to change positions, but there's always going to be 2 people. So what this could look like is a blue guy over here and a red guy over here. So they're going to change positions, just like some of the water is going to refreeze and some of the solid is going to become a liquid, but there'll always be 5 people on this line if 1 person exchanges each line at the same rate. So look at our choices. H2O melts faster. No, it cannot. They have to melt and freeze at the same rate. Freeze faster. No. the mass of water must equal the mass of liquid. Well, that is never going to happen, or it's hard to happen. If you did a tank demonstration in your school, okay, which I have one on the YouTube channel, equilibrium was attained when the water level stayed constant, which leads me to number 4 is the answer, because the mass of the liquid and the mass of the solid remains constant if they're trading places at an even rate. So 20 is 4. At equilibrium, the rate of the forward equals the rate of the reverse, and because of that, the amount of the reactants and the amount of products are the same. Number 21. A molecule of an organic compound contains at least one atom of carbon. Okay? Organic chemistry is a chemistry of nonmetals, but specifically the carbon chain. Everything surrounds the longest continuous chain of carbons. So if I've got this guy right here with the right number of H's for dashes, this will be 2-chloro. We go 1, 2, 3, 4, butane. Now, I'm not getting the organic naming, but everything surrounds the parent name. Table P tells me there's 4 carbons in my chain, and of course, the bonds in between would end in ane. Okay, so we always end our organic compound with how many carbons and how they're bonded to each other. Therefore, it surrounds carbon. Carbon is the backbone of organic compounds. So, of course, it's choice 1. Number 22. In a chemical reaction, the difference between the potential energy of the products and the potential energy of the reactants is equal to, okay, well, I hear potential energy in reactants and products. I think potential energy curves. And I suggest, in this kind of question, you draw one. Now, I'm going to draw an exothermic reaction. You should know this is the reactant side, this is the products, and energy drop down. In fact, you should know the difference of where you start energy and end in energy is something that we call delta H, called enthalpy, or heat of the reaction. Now, what does the problem say? Now that I have drew myself a potential energy curve, and you could have drawn an endothermic curve, it still would work out. But let's see what we have here. The difference between the potential energy of the products, that's going to be, let's do a new line. This line, it's the energy the products have. This would be the 0 line, so it's this high. And the potential energy of the reactants, well, that's this line. Well, I just kind of gave it away. So the difference between this line, this could be, let's say, 100. This line could be 10, not drawn to scale. So the difference between these two would be, well, 90. And that, of course, is delta H. So it's the heat of reaction. Now, heat of fusion, don't confuse that. Heat of fusion is H of F. That's the amount of energy it takes for a solid to melt. And also, it's the energy that you would use in a cooling and heating curve, okay, when the phase change, when you're at a phase change temperature. So you'd be at this point. Any case. So it's the, what happened here? It is the heat of reaction, also called delta H. Sometimes you'll see it like this as well. Sometimes called enthalpy. Okay? So in any case, the difference where you start and finish, there it is. Activation energy, since we're there, is the energy it takes to start a reaction. That's your forward. This would be the reverse activation energy. Entropy is delta S. That's chaos. Number 4 is your answer. Number 23. A carbon-carbon triple bond is found in a molecule of, well, the prefix is how many carbons, okay? So all these buttes tell me that they're all 4 carbons, and I get that from table P, but that's not what I'm after. Which carbon chain has triple bonds between the carbon? So what I'm going to do is go to a table Q, and it's going to tell me something about these ending names. Okay? All right, so let's go there. Okay, here's table P where the prefixes come in. The but is 4. Not part of the problem, but good to know where that is. Okay, so table Q tells me the ending name of my homologous series. Homologous just means the same type of bonding between the carbon. So if you've got carbon chains, it's organic compounds about the carbon. If they're single bonded between the carbons, they end in an ane. That's why they call them alkanes. If they're double bonded, they end in ene. That's why they call them alkenes. If they're triple bonded, they end in ines for ethine. Notice they're using eth for 2 carbons, which is given to you in table P. And then, of course, it ends in the appropriate ending, either ane for single bonded, ene for double, triple bonded. So they wanted a 4 carbon, or they talked about which one had triple bonds. It has to end in YNE. Now, there was an one in one of the choices. That is a ketone. If you go to table R, these are called functional groups, and if they end in one, that means you have an organic compound, some carbons attached to this, some more carbons, and in the middle you have a carbon double bonded to an O. Of course, that's not the answer. Our answer is, so the triple bond is the butene. The YNE means that there's a triple bond between 2 of the carbons in the 4 carbon chain. Okay? And it's very, very unsaturated because it does not hold the maximum amount. Okay? Double bonds. All right? Notice I'm missing some H's here because I'm using up some of the bonds in between the carbon. Number 24. Which statement describes one characteristic of an operating electrolytic cell? The key here is electrolytic cell. It's not a voltaic cell. This is the one with electricity. This one needs energy. So this is the non-spontaneous, reaction that requires a battery. So it does not produce electrical energy. That would be the battery or the voltaic cell. Okay. It requires an external energy source. Yes, because it is non-spontaneous. So 2 is the answer. Okay. It doesn't use radioactive nuclides, and it doesn't undergo a spontaneous redox reaction. Spontaneous would be the voltaic cell or the battery. Number 2 is the answer. Number 25. Which compound, when dissolved in water, is an arrhenius acid? Now, this person, has the most simplified version of all the acid-base definitions. So if you forget his name, it's easy to remember because what makes an acid an acid? Well, protons. And the only thing positive in solution, the most simplest version or definition we can have is H pluses in solution. Okay, so when dissolved in water is an arrhenius acid. So who has protons to give? Well, there it is. All right, HCl is an arrhenius acid because it has a proton that it can give to a solution. Now, it's not donating protons. That would be the Bronston-Lowry definition, which the Regents calls the other definition. This is an alcohol, from table R. This is a salt, and this is a base. This would be an arrhenius base because this will break apart into a hydroxide. And to be an arrhenius base, you have to have bases that produce hydroxides as the only negative ion in solution. So, very simplified version of any acid-base definition. Arrhenius is the most simplest of them all. Produce H pluses. The only one here that can is choice 2. And don't forget, you do have a table of acids. Let's go there now. So table K, and look at that. Hydrochloric acid is named. Look at all the H's in front, showing that loves to give up the proton. So all of these acids are arrhenius acids. Even the acetic acid. Table L, look at these hydroxides. These are salts, ions with hydroxides. They have hydroxides to give, arrhenius bases. This one is not because it does not have a hydroxide that it can give or put into solution, but it does react with water to produce a hydroxide when it accepts an H. This is the other definition. So again, 2 is the answer. Number 26 is very much similar to 25. An acid can be defined as, well, this is the other definition. It can be defined as an H plus donor. Let's say you forgot everything. Well, what does HCl do? Doesn't it? If I had HCl in water, you should know that H pluses are donated to the water, and then we make that conjugate base, what's left over after the acid gives the proton, and then we have that water with an extra proton, or H+, is called a hydronium ion. So acids, yes, produce H+ in the simplest definition, but in the Bronson-Lowry definition, which they do not name here, okay, this definition, it's a H+ donator. That's something you could definitely work through. It's logical. H+'s give off, acids give off H+. Well, acids will donate their H+. Okay, it's a better definition. Okay, this donor, I'm sorry, so an acid is an H+ donor, and bases are actually H+ acceptors. Okay, like a hydroxide is a base because it can accept an H+ with its lone pair of electrons. And that's why hydroxides act as bases. They go from OH, they accept a proton, and look what they do. They become water. H+ plus OH equals water. Any case, the answer is 2. An acid is an H+ donator, and an Arrhenius acid is one that has an H in it to give off, or at least make H+ in solution. 25 is 2. 26 is 2. Onward, okay, to 27. Which nuclear emission has no charge and no mass? Okay, I've got alpha, beta, positrons, gamma. Well, if I don't know, table O will tell me. Let's go to table O. Okay, table O is right here, and when I look at my particles, I find my gamma, because my gamma has no mass and no charge, right? So it has no mass and no charge, and that's why my gamma radiation is the winner, right from table O. All you had to do is know where to look. An alpha particle from table O is a 4, it's a helium nucleus. Beta particle is that electron, almost zero mass, -1. And a positron is that anti-electron particle, no mass, E +1. So these all have charges. That's the bottom number. And they all have mass. Even these guys with a 0 have a little bit of mass. Okay, but it's the gamma ray, or the gamma symbol, with no mass and no charge. That's the winner. Choice 3. Number 20. Which process can 10 milliliters of a 0.05 molar HCl solution be used to determine the unknown concentration? Hey, this is a titration. There's many types of titration. This is a volumetric. This is an acid-base, strong acid, strong base titration. Don't know what else to say about that. You should have done one in lab, and we certainly did. And titration's a very, very, very precise laboratory technique where we use one chemical's information, okay, to answer questions about another. Evaporation we're doing here. Distillation is separations based on different boiling points. Filtration is separating a solid from a solution or precipitate. Titration is a word where we use one chemical against another that we know to figure out that chemical. Another form of titration, by the way, it's called a gravimetric titration, is when we use the hydrate lab. You had a hydrate, and you use the mass of the hydrate. Okay, after you heat it, became an anhydrate, which was a light compound. And of course, by knowing the hydrate's mass and now knowing the anhydrate, the dried compound, the difference, of course, is the water. So all you have to do is, by using one piece of information, you can get the percent by mass of the water. It's different, but certainly titrations are using one chemical's information that we do know. In this case, what we knew was the concentration of the acid and the volume, okay, to know how much of the other chemical we need when protons and H+ are added together. But a very important laboratory technique that you should have done in class. Number 4 is titration, choice 4. Number 29. Which radioisotope is matched with its decay mode? That means which radioactive material is correctly giving off the type of particle or energy from its nucleus to become stable. Alright, so if you don't know this, okay, which I doubt that you do, then you'd have to go to table N to see that. So we'll go to table N in a second. Hydrogen 3 is gamma, K42 is a positron, N16 is alpha, and phosphorus 32 is B negative. So we're trying to figure out which one is correct. Let's go to table N. So there it is, phosphorus 32. Okay, its decay mode is B negative. B negative, what is that? B negative is a beta particle. And to know that, all you have to do is go to table O, and you'll see that a beta particle, table O of the next page, okay, is this particle here. So there's the symbol, its information. Potassium 32 undergoes beta decay. So the answer is choice 4. I just looked on table N and matched it. Now they could have changed this symbol with this, 0E negative 1, and that's why I went to table O to see that, but I didn't have to, so number 29 is 4. Number 30, which reaction is accompanied by the release of the greatest amount of energy? Wow, the most exothermic. Burning of propane, I know that gives me a lot of energy. Electrolysis of water, wait a minute, electrolysis requires energy, right? Electrolysis, as we talked about, is a non-spontaneous process that requires, this is endo. So this better not be one of your choices, no way. Okay, oxidation, 10 grams of iron, well that would be iron rusting, and that could be something that's very exothermic, but man, I'm looking at a nuclear equation. And when you mess around with the strongest forces in nature, protons being held together by something called the strong force, okay, there's no greater change in energy than the energy released or the energy changes in nuclear reactions. So nuclear fission, that's where the atomic bombs that we talked about are made from, or the nuclear reactors. So clearly the winner here is a nuclear reaction. Remember, the bomb dropped in Hiroshima. All the bombs dropped on World War II, conventional, okay, equaled the power of one bomb. So nuclear fission, okay, clearly gives off a lot more energy than any other chemical reaction. Chemical reactions, okay, not nearly the same type of energy. So number 3 is the answer for number 30. Number 31, total number of protons, electrons, and neutrons in each of the 4 different atoms are shown in the table below. Which two atoms are isotopes? Isotopes, my friends in chemistry, are the same atom. If it's the same atom, it's the same number of protons. So I'm looking for the same number of protons, okay, same number of electrons, because it is an atom, which we should learn is neutral, okay, but different number of neutrons. So A and D are going to be your answers. These guys have same protons, same electrons, that's why it's an atom, it's neutral, but different number of neutrons. Okay, if I was to draw them, okay, you'd realize that atomic number 6 is carbon. So carbon, okay, in this case, 6 plus 7 is 13. In this case, 6 plus 8 is 14. So what you're really dealing with is carbon 13 and carbon 14, sometimes drawn this way. These are isotopes. They're both carbon, both have 6 electrons, 6 protons, but different mass number. The mass number is the protons and the neutrons. So for me to get 13, all I did was add the protons plus the neutrons. Okay, any case, A and D, same protons, and that kind of gave it away. Different number of neutrons. Number 31. Which Lewis dot diagram represents an atom in the ground state for a group 13 element? Let's go to group 13 on the periodic table and see what we have there. So here's group 13, and if you already figure it out, it has 3 valence electrons. One little trick, take the 1 away, but you can also look at the outermost electrons here. These are the outermost electrons. Okay, these all have 3 valence electrons. So we only care about in Lewis dot diagrams how many electrons are available for bonding. The other two electrons in the case of boron we don't write in a Lewis dot diagram because these guys are stable. They're core electrons. They're held very tightly to the vest of the protons in a nucleus. It's only the unstable electrons that are not any filled energy level that are available for bonding. So aluminum, boron, anybody in this row is going to have 3 dots. Each dot represents a valence electron. So group 13 has 3 valence. Therefore, 3 dots. Okay, and that's why choice 3 is the answer. Number 33. Which element forms a compound with chlorine with the general formula of MCl? That's a 1-to-1. Well, if I draw this out a little bit, well, this guy has to be positive. It's in front. The one at the end has to be negative, and chlorine only has one negative choice. But if we're not sure, we'll go to the periodic table. So chlorine has a bunch of states it can be, but you can see it only has one negative choice. The one in front has to be positive, so this is clearly -1. Therefore, this M, this metal, is +1, right? -1 + 1. These things have to equal 0. So which element has a +1 oxidation state? Okay. Rubidium or radium? Well, the answer is going to be 1 because rubidium is a group 1 ion. Okay? But if you don't know that, with its rate on a rubidium, you look in the reference table. Which one only has one? Which one has a +1 state? So we go to the periodic table, and we can see that clearly a rubidium has that -1 charge. Okay? Radium, okay, which is a group 2 element, as a +2. Remember, group 1 ions only have one choice, +1. Group 2 ions, notice the group numbers are all +2. So the one that becomes +1 is rubidium, and it's proven there by its oxidation state. Okay, 34. A sample of an element has a mass of 34.261 grams and a volume of 3 cubic centimeters. To which number of significant figures should the calculated density of the sample be expressed? Well, density is mass over volume. Now, if you didn't know that, believe me, Table T will show you that. I'm not going to show you that, but Table T has it, okay? You should know density is mass over volume. However, if you don't know, you could have went to Table T. Now, the mass is 34.261. And there is a point there, and I am making a point. All right. And you can divide by the volume, which is 3.8 cubic centimeters. And when you divide or multiply, okay, we call this the accuracy rule. Way back when, we do the answer and we divide by the least number of significant figures to maintain the accuracy of our number, because we are subtracting, okay, some error here. Okay, we guessed here in the thousands place, we guessed here in the tenths place. So our number that we're going to reflect in our answer could only have 2 sig figs because our least significant number has 2. The weakest link, okay, is 2 sig figs. So we round off our number to the least number of sig figs. And of course, they're just asking, well, how many sig figs will that be? And that'll be 2. And you divide or multiply, you round off the least number of sig figs. The reason's very simple. We have some insignificant numbers that we're putting through the calculation. Think with me for a second. I've got a number that I'm not sure of in the thousands place, and I got a number I'm not sure of in the tenths place. You take this big number, which is a guess, and divide it by this number here. This is going to make the rest of the other numbers hard to really, really believe in, because you're using a guess part of a number to do the calculation. So to control for numbers that may not reflect the true accuracy of the number, because this is a guess and a big guess compared to this one, we round off by the weakest link with 2 sig figs. So the answer is 2. So if this is multiplication or division, you'd be rounding off least number of significant figures. But if this was addition or subtraction, like 11.017 plus 1.1, here we're going to round off the least number of decimal places. This is the precision rule. So let's add these together. and this would be 12.117, and we round off to 1 decimal place. This becomes 12.1. It's the precision rule. So when you add or subtract, round off least number of decimal places. Multiply or divide, round off least number of significant figures. Answer is 2. Number 35. Which characteristics both generally decrease when elements in period 3 of the periodic table are considered in order from left to right? So when we go to the periodic table, going left to right, we know that we're becoming more like non-metals. We should know that metals have big radii, non-metals are smaller because they attract their electrons in closer. So as we go from left to right, the non-metallic properties increase because the radii get smaller because the nuclear charge can pull them in. If you're pulling in electrons, it means your electronegativity is higher, and it takes a higher amount of energy to pull electrons away. It's the ionization energy. So non-metals exist smaller, metals are larger. So you should know, going across the periodic table, the non-metallic properties are clearly increasing. Okay, that's where the non-metals exist, on the right side of the periodic table. So what's decreasing? Then the metallic properties are decreasing if you're becoming less like a metal. So the metallic properties are decreasing, and the atomic radius is decreasing. Metals are big. Okay, now if you need to, Table S can show you a lot of these, but this is a really great question. Understand the periodic table is based upon a couple different things. Non-metals above the staircase, big atoms over here, so over and up are your non-metals, smallest atoms, most electronegative, highest attraction. Down to the left, more metallic. Radius decreases. If you don't know that, Table S could show you that. Okay, if you were to go to Table S, okay, you would do that, and it would have those atomic radii. Number 35 is 3. Number 36. Which formula is both a molecular, how it exists in nature, and empirical? Empirical is lowest ratio. So for instance, and as an example, hydrogen peroxide, H2O2, that's how it exists in nature. That's the molecule. It's exactly how 2 O's bond together with an H. It's a little bent here because of lone pairs. Okay, it exists as this particle exactly. But if you were to what? Find the lowest ratio, that would be what? 2 to 2 is really 1 to 1. It would be a HO. Okay, so clearly I'm looking for something that's already the lowest ratio that can exist in that lowest ratio. So glucose, and that's sugar, you should recognize that. That's a molecular formula, but its lowest ratio is CH2O. That's the empirical. This can be reduced to CH2O, and this can be reduced to C2H4. The only thing that can't be reduced is C3H0, and that's the answer, because if you've got 3 C's, okay, you got an O in here somewhere. Okay, so we have 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that O is probably in between these C's as an ether. Oops, excuse me. So let's get rid of this right here. So that O is probably in here as an ether on either side, and that's how we get something that can exist, which is called molecular, but it just so happens to be the lowest ratio. But if you didn't know any of that, the only one with the lowest ratio is choice 3. Number 37, an atom of argon in the ground state tends not to bond with an atom of a different element because argon has, well, argon, my friends in chemistry, is a noble gas. It's got a stable configuration. All the noble gases have very stable electron configurations. Now, stable means they have low energy, which means they're going to stay in that state until you add a lot of energy to destabilize them. So they are not going to bond because they naturally have the electrons necessary to make them stable. Most atoms do not, so they bond to achieve electron configurations that are stable. Things in nature usually go from high energy, which usually means unbonded, to lower energy, which is bonded. In any case, okay, argon has a total of 8 valence electrons. Okay, and that just means it has a stable octet. That octet, so argon, okay, is 2-8-8, and there's something special about having that 8, okay, which is the S and P being filled, but that's not part of this course. But this has the configuration, that 8, called the octet rule. So when you draw argon electrons dot diagram, you see, Mr. Grodsky, argon has no valence. It's a noble gas. Well, true, but we draw the 8 to show that argon has that 8 filled. Having that octet, okay, gives it a very stable configuration. Therefore, it doesn't bond with much. Choice 4. Okay, number 38. Number 38, which formula represents a molecule having a nonpolar covalent bond? Nonpolar covalent bond means that we're sharing electrons equally, okay? So in the New York State Regents, okay, we're looking for bonds that are sharing electrons equally. They have to be the same atom with the same electronegativity. That's how that's going to work. So all of these bonds that I'm coloring in are going to be polar covalent bonds because they're sharing unequally because they have different electronegativity. So a carbon to carbon, both with an electronegativity of about 2.6, if you look on the electronegativity table, table S, having the same attraction for electrons, the pair which represents one bond is being shared right down the middle so that no side of the bond has more electrons than another. So that's why we say it's nonpolar. Case in point, H2 is nonpolar. I2, when you bond to the same atom, okay, you're sharing electrons right down the middle. And that's going to create a nonpolar covalent bond. The carbon to hydrogen bond in the New York State Regents is considered to be a polar bond because carbon has a 2.6 electronegativity, hydrogen 2.2, so this pair is being pulled closer a little bit slightly to the carbon side, so that's a polar bond. However, you know the rest of the world considers a carbon to hydrogen bond to really be a nonpolar bond. So the best answer is choice 3. Okay? Number 39. Number 39. Which compound has the lowest vapor pressure at 50 degrees Celsius? All right, well, lowest vapor pressure. Well, vapor pressure is the rate of evaporation. How well does something evaporate? Now, if you have a liquid, how well does that liquid escape into the gas phase? And if it does, it creates a force upward. So vapor pressure is really a measure of how well something will evaporate. So I'm asking about 4 liquids and see who is going to evaporate faster. In fact, if you remember very carefully, I did a demonstration, I should say, of ethanol, propanol, and water, and I put them on a desk, and we saw which one actually evaporated. Okay, so if you don't remember that experience, that's okay. There's a place we can look to find that. Let's go there right now to table H. Let's go to table H now. Okay, table H, here we go. Okay, in all of its glory, table H, and look at the 3 liquids. Propanol, which is another fancy word for acetone, okay? So I was using acetone, which is the common name. Propanol means you have 3 carbons with an one, which is a ketone. Ethanol, the OL ending, means we have an OH group at the end. Water, dihydrogen monoxide, careful that stuff. Ethanoic acid, that's vinegar or vinegar. Okay, that's the carboxylic acid group. Doesn't have to know, but table R, you could look up these guys to figure out what they are in table R. Any case, okay, at 50 degrees Celsius, okay, which liquid has the greatest rate of evaporation? And by drawing a line, and you don't have to, you can clearly see that this liquid at 50 degrees Celsius evaporates much faster, and that's the one that almost disappeared as soon as I streaked it across the table. So propanol has the highest vapor pressure or rate of evaporation. Now that's the answer, but you should also know it has the weakest attractive forces. Propanol doesn't attract other propanol molecules very strongly, so these guys are able to evaporate the liquid. The one with the stronger intermolecular attractions is water and ethanoic acid. They resist evaporation. They take a lot more energy or temperature to force them to evaporate. And of course, this dotted line here is the temperature at which they boil. Notice water boils at approximately 100 degrees Celsius. That's when the vapor pressure upward equals the atmospheric pressure. So propanol is your answer. So here we go with propanol, highest vapor pressure, choice 3. Number 40. Given the potential energy diagram and equation representing the reaction between, a potential energy diagram. I'm loving it. Yeah. So let's see what we have here. Sounds of summer in the background, of course. Okay, given the potential energy diagram equation representing the reaction between substances A and D. Now, the first thing I'm looking at this is, hey, we're starting low, going high. Somehow we had to absorb energy to make this happen. This is endothermic. Okay, so in any case, let's see what the question reads. According to table I, okay, so I guess we have to go there. Substance G could be, well, think with me for a second. This is a formation reaction or a synthesis reaction. This is that heat of formation table that the Regents has tried to put together. So making a compound from its elements, and boy, that reaction looks endothermic, which means you're starting here and you're going high. The delta H is going to be positive for endothermic. So I'm looking for a reaction when it's making one thing, the delta H will be positive. The energy is rising. Okay, the products have more energy than the reactants because of that absorption of energy. So which of the following choices, when it's made from its elements, is endothermic? HI, H2O, CO2, or C2H6? Let's go to table I and find out. So here we are in table I. And the top part of table I are combustion reactions, O2 with some carbon-based fuel. And as we rotate down, the middle part is that formation or that synthesis table, and we're looking for a synthesis of the choices which are endothermic. Making water, okay, no matter if it's a gas or a liquid, is very exothermic. Okay, making CO2 from its elements, also exothermic. Okay, making HI, hydroiodic acid or hydrogen iodine, that is our endothermic one. I think the C2H4, C2H6 is exothermic. So of our 4 choices, the one that's different, or a positive delta H, okay, is the hydrogen iodide. But if you forget what's exo and endo, even though this question had 3 different, okay, look at the bottom of table I. Don't forget, they're telling you a minus sign indicates an exothermic. Remember, your curve was endothermic. Well, I'm sorry, was endothermic, starting low and going high. So that told you it was positive. So you had to read that curve carefully. So back to the question. So all of these choices, okay, are exothermic except for HI. Number 1 is the answer. Okay, so clearly it's choice 1 is HI. It's the only one that's different, but it's the only one that's endothermic according to the endothermic curve, which you should be able to identify. Okay, number 41, moving right along here. A sample of a gas confined in a cylinder with a movable piston is kept at constant pressure. Okay, the volume of the gas doubles when the temperature of gas changes from. So now we're thinking about, we're at constant pressure. We have this relationship of pressure volume over temperature equals pressure volume over temperature. Now, sometimes I go vice presidents or VP, but what's staying constant is the pressure. So we're going to get rid of that, and as I've taught you with mathematical equations, you cross it off. Okay, probably don't want to do that. Okay, oops. Okay, I'm going to cross it off. Get the P away, so now it's volume temperature over volume temperature. So volume and temperature, okay, is directly proportional. Okay, so and you may not be able to see that in the equation, but as temperature goes up, okay, so as temperature increases, all right, the volume has to expand. As you make gas molecules go faster, they're going to collide more often, and they're going to push on the walls of the container more, and they're going to expand. In this case, it's a piston. So you've got, let's put the piston on its side. So you got a piston and its top, and you got the cylinder here. And you got a confined gas with a certain number of molecules. Make them go faster. These guys will collide more often, and it's going to push this cylinder outward, and the volume's going to expand. So look at your choices. So when the temperature of the gas doubles, okay, I'm sorry, when the volume of the gas doubles, okay, the temperature of the gas should also double, okay, according to Kelvin temperature, because the gas law is based on an absolute, okay, absolute temperature. So we know temperature, all right, and volume are directly related, called Charles' law, and it goes right through the y equals x line, but this has to be Kelvin temperature. They're directly related if you're in kelvins. Okay, it's absolute 0 point. Okay, so we can't get rid of the Celsius. And we look at who's doubling. Temperature's doubling here, choice 2. Okay. Now, if you want to use the equation, you can. If you were to put a value in here, okay, if you were to put a volume in here, let's put 1 liter, okay, 1 liter, and the volume of the gas doubles, so this would be a 2. Let's change the ink. So this is a 1, this is a 2. When the temperature does what? Okay, well, think with me. 1 to 2, so this is a 1. Okay, this would have to be a 1, and this would have to be a 2. Like, they're equal to each other. So as the volume doubles, so would the temperature. Okay, and you could solve for that. But again, the direct proportion that we learned already, okay, should be the key. And again, it's based on Kelvin temperature. Choice 2. According to table F, which compound is soluble? So they're telling you where to look, and we're looking for solubility issues here. Solubility means that, hey, we dissolve into a water, which makes a solution. So barium phosphate, calcium sulfate, silver iodide, sodium perchlorate, which one is soluble? So let's go to table F. Okay, so our solubility rules. Let's look at barium phosphate first. Let's go find some phosphates. Now, phosphates have a high charge, so phosphates, okay, phosphates, all right, are -3, and they are normally insoluble. There are some exceptions, but barium is not a group 1 atom, it's a group 2 atom. It's in the second column, so barium phosphate, okay, is not soluble. It'll be insoluble. And a +2 and a -3 are really strong charges, hard for water to compete for that. Calcium sulfate, okay, these guys are normally very soluble. And then, of course, there's some exceptions, right? So they're normally soluble, but with calcium, it's an exception. So this is supposed to be soluble, but calcium sulfate makes it insoluble. Okay, next one we're going to look at is silver iodide. Okay, iodide is a halogen, and just as you see here, it's soluble, except with silver. So it's usually soluble, but the exception with silver makes it makes it insoluble. So it has to be the perchlorate, which is listed, is actually not listed. Okay, so I guess if you notice, the perchlorate is not listed. Okay, so therefore, by just process of elimination, it's going to be the perchlorate. However, if you look carefully, let's go back to the problem. It's sodium perchlorate. That's a group 1 ion, and something about table F says that all group 1 ions are soluble. Let's go there. And here we are. Group 1 ions are always soluble. There are no exceptions. So even though the perchlorate's not listed, okay, this one's going to be soluble, because if you've got a group 1 ion, hey, it's soluble. And we know why. Charge density is so low as these big ions. So obviously choice 4 is the answer. So obviously number 4 is our answer. Number 43. Number 43. Given the equation representing a system at equilibrium, which changes occur when the temperature of the system is decreased? Well, if I'm at equilibrium, the rate of the forward equals the rate of the reverse. However, if I apply a stress, I'm going to make one of the directions, forward or reverse, faster, because what I'm going to do is I'm going to stress it in such a way to make it fall out of equilibrium. Okay? So what happens is we have a reaction that is nicely in equilibrium. We apply a stress. That's what this is, the stress. And what happens is the reaction responds so that it doesn't fall over. So what I mean by that is, if you're a person standing high and I push you with my big hand, okay, you're going to fall down. Unless you do what? You push back with your back feet the opposite direction. That is what Le Chatelier's principle is. We apply a stress to a reaction that's nicely in equilibrium, rate of the forward equals rate of the reverse, and that stress unbalances the reaction, and the reaction regains its balance by doing the opposite so that it doesn't fall over. Okay? So the stress here is that the temperature is decreased. So the reaction is going to respond by doing the opposite by increasing the temperature. It's going to do the opposite. Now, how can it increase the temperature? It can do one of two things. It can go in the forward or in the reverse. Well, the forward direction is exothermic. The energy is on the product side. So if we lower the temperature, we just unbalance the reaction. It regains its balance by increasing the temperature to get at equilibrium. And the way it increases temperature, it favors the exothermic way. It can only shift right or shift right to regain balance, but it's going to shift right, which means the forward reaction is now faster than the reverse, so that we increase the energy or release enough energy to increase the temperature of where it's supposed to be. Okay, so if that's the case, we know that the forward reaction is now faster than the reverse, or it shifts to the right. We know N2 gets used up, H2 gets used up, and we're going to make more ammonia, NH3, and of course more energy. Notice these are on the same team, on the same side. So what happens is the concentration of N2, okay, and the concentration of H2 increases. That wouldn't make any sense because we're using it up. Concentration of H2 decreases, that's correct, and N2 increases. That doesn't make any sense. They would both do the same thing. They're both on the reactant side. Number 3, the concentration of the H2 decreases. Okay, yes, and the N2 decreases. So no, NH3 is going to increase as we move to the right to make more of it. So 4, I think, must be the answer. The concentration of H2 decreases, and the concentration of NH3 increases. That's the correct answer. Choice 4 is your answer. Which formula represents an unsaturated hydrocarbon? Now, unsaturated means that we can hold or gather more H's to the carbon chain when we open up a double bond. Okay, something with a double or triple bond holds what? Less H's. What's the general formula of this hydrocarbon? This hydrocarbon is C2H4. Now, if it had single bonds, it would be 2 C's, and look at that, a lot more H's. Okay, a lot more H's. Why? Because of the single bond. There's more room to add H's. With a double bond, you're locked into less H's because carbon makes 4 bonds. So we're looking for something with a double or triple bond, okay, between the hydrocarbons. This is saturated. Alkanes are saturated. This is also saturated. Okay, single bonds between the carbons. So as you probably have already seen, this is not saturated. Okay, this is unsaturated. And the reasoning behind that is because, well, if I was to take away that double bond, couldn't I theoretically add 2 more H's right here? So if this was a single bond, so because it's not as saturated as it could be, so it's unsaturated. Looking for an alkene or an alkyne. From table Q, it shows you that. Okay, so choice 3 is the answer. Which half reaction equation represents the reduction of an iron to ion? First of all, that stock system, Roman numeral 2 means we're dealing with iron plus 2. It's the actual charge. Why do we need it? Because iron can be plus 3 as well. You go to reference table, you'll see that both ions exist for iron. And of course, there it is, the two choices that iron can be. So when you have an iron, you have to tell me which one you have. Same thing with the rest of the transitionals. However, if you had something from the group 1 or group 2, they only have one choice. Therefore, they don't need that Roman numeral system. Back to the question. Okay, so we know that we're dealing with iron plus 2. So we're dealing with either 1 or 2. These will not happen. Okay? So the question is, which represents the reduction of an iron to ion? Well, reduction means gaining electrons, right? Because you have Leo the lion says grr. So grr means gaining electrons is reduction. So electrons will be in the reactant side. Besides, reduction means that your charge goes down because you're gaining negative. So this plus 2 goes to 0. So that's why choice 2 is the answer. Okay? If you look at choice 1, you're losing electrons. This is oxidation, not reduction. Your charge is going up because you're losing negatives, right? Because Leo means losing electrons. If you lose electrons, you would be on the product side. So choice 2 is the answer. Number 46. Which metal is more active? Now, when they say active, we can always put a re in front. Reactive. Okay, reactive means it's going to do something. It's unstable than H2. So which metal? Well, we've done a few labs with metals and their reactivity, but if you forget, there's a place to look that shows how metals are reactive. Now, what do metals do? All metals, when they're zeros, when they're atoms, as listed as these choices, these are all standalone elements, so they're zeros. You guessed it, they become positive something. And they do so by losing electrons. Metals are big. They lose electrons. Okay, the ions get smaller. Okay, so really losing electrons, Leo, the lion, it means they oxidize. So let's go to table J, will help us. Okay, here's a list of our most active or reactive metals, and as you go down, their activity decreases. Okay, so least reactive, and of course the most reactive. So we want to see which one's more reactive than H2. So I look at my H2, okay, and I'm looking for an element above. Notice copper, silver, and gold are below H2. The most reactive element or metal, the one oxidized the best, is the one higher. It's the one above H2, so lead is our answer. So there we go with our answer. Okay, answer 4. Okay. Number 47. Given the balanced ionic equation representing the reaction in an operating voltaic cell, this is a battery. Alessandro Volta and Luigi Galvani, these two Italian scientists, together collectively with their discussions and arguments, created the battery. Okay, so this is spontaneous. Now look, zinc 0 goes to zinc plus 2. We have two metals involved, two solids. The flow of electrons through any redox reaction. This is redox now. Okay, this part of the test is redox. How do I know? Well, look at the last couple of questions, 45, 46, 47. Notice the test kind of goes in order of the units that we learned. So this is redox because I see zeros in the reaction. And no matter if it's a battery, electrolytic cell that needs electricity, electrons always flow from one way to the other. And it's total common sense. They flow from the chemical that what? Loses electrons to the chemical that gains them. It's the only way they can flow. Doesn't it make sense the one who loses has to flow from, and the one that has to gain is the one? So it's the one who oxidizes to the one who gets reduced. And we have a mnemonic for this. Anox, red cat. So anox, red cat. So what does that tell me? We have the anode is the place of oxidation, and we have that cathode is the place of reduction. So electrons always flow from the anode to the cathode, from the place that loses electrons, oxidation, from the place that gains them, reduction. So it goes from the anode to the cathode. The question is, which one is correct? Now, never, ever is it the cathode to the anode. That can never happen. How can you flow electrons from someone and gaining them? So these are silly, silly, silly questions. The question is, who is the electrode? The zinc or the copper? Okay, well, if you've done enough of these kind of questions, or you've done the lab, you know that one of these two is higher on table J. The first step, we go to table J, so let's do that. The metal that is more reactive is the one who oxidizes. So the higher on this table is the one who is the anode, right? And ox. So the one who is higher on this chart is oxidizing. So we've got zinc and copper. There's my zinc, and as you probably have already guessed, the copper is lower. So this is my anode. The metal that's higher on this table, that's better able to lose electrons, is oxidation, and ox, the anode, is oxidation. So the zinc is the anode. So it's from the zinc anode to the copper cathode. Choice 3. Which laboratory test can be used to determine if KCl is an electrolyte? What is an electrolyte? There's three things: acid, bases, and salts. And what makes them conduct electricity, as you probably already know now, is free ions, mobile ions. So if we want to test to see if KCl is an electrolyte, determining its pH, which would be 7 because it's not an acid nor a base, would not tell me if it's an electrolyte, because acids and bases definitely are electrolytes, but are also salts, and some salts are neutral. So that doesn't make any sense. Okay, the pH of the solid doesn't make any sense. Yes, the electrical conductivity of the aqueous ion. Number 4 makes absolutely no sense. A solid ionic compound never conducts because the ions are not free. They're locked in these crystal lattices of ions, the positive and the negative ions, and they're not free to move. You have to have ions moving. So choice 3 is the answer. And we did this. We put a light bulb, okay, and their leads into solutions. And you saw that the salt solid didn't light it up, but when I added water, the ions were free to do so. Choice 3. Number 48 is 3. Number 49. Number 49, which compound is produced when HCl is neutralized by calcium hydroxide? Hey, neutralized. Acid-base reaction. Acid and base makes what? Salt and water. So let's write it out. Hydrochloric acid, calcium hydroxide. Okay. And what's going to happen? Well, it's a double replacement, or an example of. H is positive, chlorine is negative, the calcium is +2, each hydroxide is -1. Well, they're going to switch partners. The H plus from the acid hooks up with the hydroxide to make HOH, or water. However you want to write that, this is acceptable. And of course, the calcium +2 will attract the chlorides and make calcium chloride. And there's your acid. Okay, HCl is your acid. And base make your salt and water. So which compounds? They could have put water, they didn't. Okay, but the salt made is calcium chloride. Basically, it's a double replacement reaction. Okay, now I didn't balance it. Okay, if I had to balance it, there's 2 hydroxides here, so I'm going to throw a 2 here. Gives me 4 H's. I'd have to throw a 2 here, and now I'm balanced. Okay, last question. So the answer is choice 1 for 49. And the last question, the multiple choice, number 50. Which nucleides are used to date the remains of a once living organism? If something was once living, it has organic origins. And something that's organic has carbon. And we know that carbon-14 is a radioactive isotope used to carbon date things like the Shroud of Turin, all right, Turin, which is supposedly the Shroud of Jesus. Okay, we talked about carbon dating, all right. So it's going to be the carbon-14 to carbon-12 ratio, because over time the carbon-14 is going to give off a beta particle, right? This is 6. And if I just show you a nuclear equation, you don't have to write this, but I'm showing what happens. Carbon-14, if you look at table N, it emits a beta particle, a high-speed electron, which is really a neutron splitting into a high-speed electron and a proton and a neutrino, but we don't look at that in this course. And of course it makes nitrogen, because what number plus -1 is 6? 7. And this is 14. Notice all the numbers on one side equal all the numbers of the other. And we make nitrogen. So over time, carbon-14 will decay into nitrogen. And you'll have less of it. And we know the half-life, all right, of this carbon-14, the amount of time it takes for it to halve. So depending on how much carbon-14 we have left, we can get the date. So any case, cobalt-60, cobalt-59 is mostly used for chemotherapy or radiation or cancer therapy. Iodine-131 is used for tracers in human bodies, short half-lives. Uranium-238 to 206 is used to map out the age of the inorganic substance or the world. Hope you enjoyed it. Rock on.